Oh, let's start. I guess we are recording. So this is the last class, and we have covered most of the lectures, and we'll just finish up with the uh, aperture radiators today. So this was the only topic left with us. We'll see one example on this, and then we'll close today's class. So I had shared the course feedback form, which is very important for everybody to fill up if they need a course completion certificate. I'll share that again. I'll share all the material that we have covered through slides and through the lecture recordings, all the assignments I've shared. Maybe uh, I'll design one or two more assignments and share that time, but since they need not be returned, so it should be fine. I'll try to um, uh, like make a the certificates, like generate the certificates for everybody who has filled up the form maybe by Wednesday or Thursday. So, I'll close the form and then I'll generate the certificates and try to give them within a week or two. So that should be it. So by the end of this month, I think, no, by the mid of this month, I think we'll be done with all the logistics of this course, and will have your certificates with you. Okay. So yeah. So this is the textbook that we were covering, and so we are at the last module, Aperture Radiators. Uh, f- Once we are done with this course, I guess. So I've been designing the the assignments from the problems from this textbook itself. So um, you can go through the problems from this textbook and also refer to antenna theory by Balanes. I guess you guys already have the solution manual for this textbook and the and antenna theory by C. Balanes. So you can try solving problems with them for a greater grasp of the material that we have covered. Previous class, we were discussing log periodic antennas. We'll be doing aperture radiators today. Okay. So, up till now, our analysis of the radiation characteristics of antennas has been generally proceeded from current distribution. So, let me just switch this to a pen. So what up till now, what we did, we had the current distribution with us, and then from the current distribution, we calculated the auxiliary potentials, and from the auxiliary potentials, we calculated either the electric or the magnetic field, usually the magnetic field, and then from the magnetic field, we calculated the electric field, and hence we had both the fields with us. So that's how we have proceeded till now. But yeah, so from the current distribution, retarded vector potential is determined, and then magnetic and electric fields were found from the vector potentials. So in many cases, the electromagnetic radiation may have been viewed as emanating from an opening or an aperture, like for example, the very popular horn antenna. So over here, if you see directly, we do not have the current distribution with us. We do not have the current distribution with us, but we still have radiating uh, fields with us. So how do we get the radiation properties of this antenna when we do not know how the current distribution? So we definitely have oscillating current somewhere that is generating the fields, but over here we just have an aperture. So and similarly, we also have slot antennas over where we just have a slot and we do not have the current distribution with us to solve for the far field to solve for the electric field or any magnetic fields. So in these cases, we call them aperture radiators because we have an aperture, and we tend to solve them differently by using the known field distribution at the aperture. We what we do is we do a Fourier transform of the field distribution over here, and then by using the field distribution over here, we try to calculate the far field uh, properties, far field distribution. To be sure, the source radiation can always be traced to some time varying current somewhere, uh, uh, time varying current somewhere, but the current distribution are often unknown or difficult to determine or approximate. So that's what I was saying, that we definitely have some time varying current somewhere, but in case of aperture radiators, we do not have we do not know the current distribution with us, or we do not have a very good approximation with us. So in but it's definitely so if it's radiating, we definitely have some, the time varying current somewhere, but it may not be known to us. And such radiating systems are quite unlike dipole antennas and must be analyzed in different ways. So, uh, by such radiating systems, we refer to the aperture radiators we are talking about here. So, the aperture radiators are unlike dipoles, where we have very simple current distribution with us, and we can calculate the uh, properties by integrating or differentiating the field distribution, sorry, the current distribution with us. And aperture radiators, the popular ones are slot antennas, horns, reflectors, and lenses. So here is an example of a reflector. Here is an example of a lens, where we have a source over here, some kind of feed, and then this is also an aperture, and uh, then the fields traveling from the feed are modified by the reflector or the lens. So in this case, the sol we do not use the current distribution, because we do the current distribution over here at the feed or on the reflector is unknown, and as we can solve it differently. So in the case of reflector and lens, we can use the ray theory, which we probably won't be covering today, but just to let you know, we can use ray theory. And for the slot and horn antennas, what we do is we use the current, we use the field distribution that is known to us on the aperture, and we do a Fourier transform to get the fields away at a farther distance. Okay. So maybe pause at this slide and let you read this if you have any questions on this, or else we'll start with deriving the far field uh, electric field expressions for the aperture radiators. Okay. So continuing our discussion on the aperture radiators, we'll try to calculate the field properties at a far distance from the aperture by using the field distribution at the aperture. With a nearly uniform phase over the aperture, the far zone field is a two-dimensional Fourier integral of the field distribution at the aperture. So this is very important that you must remember. So if for nearly uniform phase over the aperture. So if we have nearly uniform phase of the field over the aperture, the far zone field. So this is the aperture over here. This is the aperture over here, and this is the far zone. So the field at the far zone, the field at the point P, is basically the Fourier transform of the field distribution on the aperture. So we have field distribution over here. So let this be EA, yeah, electric field distribution at the aperture, and we can calculate the electric field at P by taking Fourier transform. This is the crux of what we'll be discussing today. So once we have the field distribution at the aperture, we'll do a Fourier transform of the field distribution at the aperture and calculate the field distribution at the far zone point P. So once this is known to us, it's all maths, and we'll do that step by step now. So let the electric field distribution in the aperture outlined in figure 1132 be linearly polarized, say in the x direction. So it's linearly polarized in the x direction. Okay. So we have field distribution like this, and with no phase variation. So we have a uniform phase in the x direction. So we can write the electric field at the aperture EA as AX EA. And then if the aperture dimensions are large in comparison to the operating wavelength, then almost all the energy of the radiated field will be contained in a small angular region around the z-axis. So if this is if this particular aperture is very large, then most of the energy will be focused around the z-axis over here, and the far zone electric field at a distance point P can be written as EPAX EP. So yeah. So what we're trying to say, since if this particular aperture is, if this aperture is very large, and if this is radiating, then most of the field will be focused around the z-axis. Okay, I think I should clear this. So if this particular aperture is very large, let's say this is very large, and this particular aperture is radiating, so in this case, all the energy will be like focused in form of a beam like this uh, in uh, in in the, uh, in the z-axis. So if you remember, for like on antennas, we know that the how the field how the radiation pattern looks like. It's like this beam. So that's what we're trying to say. If we have uniform phase over here, and this particular aperture is very large, so then the radiated energy will be focused like a beam, like this beam over here, and the field at particular at point P can be written as EPAX EP. Now we have the expression for electric field at A, electric field at the aperture, and the electric field at P. Now and we know that the field at P is the Fourier transform of field at the aperture. So we can write that now. So EP is equals to J upon lambda R naught. The closed in, the integral over the aperture, integrating over the aperture, this area of the aperture, EA with the field at the aperture, and this is from the formula of the Fourier transform, and the integrands. So this is basically writing the Fourier transform of EA and we get the V. And then for beta are much greater than 1, we can simplify it. So what we are doing is, let me again clear this. Um, so what we are doing now, for beta are much greater than 1, we have to write R in terms of R naught. And what we can do is, we have this vector with us from origin to xy. We can take its component uh, in this direction and subtract it. So we are taking the vector xy and we're taking the dot product with the r naught over here, and then we get the component of r naught with this and with the component of xy in the direction of r naught, and then we subtract that with r naught to get the magnitude of r. So that's some vector calculus going here. Um, so now we have the expression for r as well. We'll substitute that in 11,158. Upon doing that, we have we, we have replaced the integral term with f theta phi, which is the field distribution and the pattern function. And now the pattern function is given as the closed integral of the over the aperture of electric field. At the aperture, and exponential of j beta sine theta x dash cos phi plus y dash sine phi. So now we have got the expression for the pattern function, and then we can use this pattern function under specific cases to get the expression for the pattern, to get the radiation pattern. I'll pause over here again and just try just summarizing this. Um, the electric field at P is the Fourier transform electric field at the aperture. Um, we and we wrote the expression for the electric field at the aperture, the electric field at the point P. Wrote down the relation of Fourier transform. Uh, Calculated the magnitude of the approximate value of R from the vector x dash y dash and and the distance r naught. Um, Subtracted that, got the simplified value of r, put that inside 1158 to get the expression 11,160, where we have f theta phi as the pattern function, and the pattern function is now given in 1161. So it's just writing down the math. The crux is over here. We have to take the Fourier transform. Um, any questions on this? So I'll pause over here for you to go through the slide, and you have any questions, you can unmute yourself and ask, or write down in the chat, whichever suits you. If there are no questions, we'll continue. So we wrote down the expression for the field at the aperture, uh, performed a Fourier transform, and got the expression for the field at a far zone point P, simplified and approximated the value of distance r from the aperture to the point P, and then substituted that to get the expression for again the field at point P and the pattern function f theta phi. And the now the equation 161 expresses rather a simple relation between the aperture distribution and the pattern function, and they are the Fourier transform of each other. So basically, the pattern function is the Fourier transform of the electric field at the aperture, and the inverse relation. The inverse relation expressing E the electric field at the aperture in terms of F enables us to determine the aperture field required to form a specified pattern function, and this is a synthesis problem. So for example, if we know how what kind of maybe field distribution that we want, do we want one lobe or do we want a three lobe? So based on so if we know the distribution with us, so what we can do is we can engineer the field at the aperture, and by doing an inverse Fourier transform, and then if and then we can achieve the desired pattern with us. So what we're trying to say is if we if we have a particular field distribution at the aperture and we get corresponding pattern function. So what we can also do is we can engineer the field distribution at the aperture to get a desired pattern function. I hope this was clear. Uh, for a rectangular aperture with a dimension a cross b, so what we are doing is we are thinking about for example, waveguide sort of thing, open or a slot uh, aperture. For rectangular aperture with dimensions a cross b, so this is a and this is b, or this is a and this is b, in the separable field distributions. So what we are trying to say is the exponential terms over here can we can uh, separate them if they are not dependent. Theta and phi are independent. So yeah, so we can write the E field as a product of F1 and F2, where the pattern function, this 1161, becomes this function over here. So we have separated the x theta x theta and phi and y. We can rearrange them to write them like this. So we and this particular function is only if it does not if yeah if we do not have a dependency of y over here and we do not have a dependency of x over here, we can separate the integrals as products, and now we have this pattern function over here. And but and what we can do now is for specific E plane or H plane, we will have phi uh, um, something over here. Yeah. So yeah, so we separated the pattern function over here, and what we're saying is, um, so this does not have any functions of y, and this does not have functions of x, so we can separate them, and and for particular e planes or h planes, what we'll have is we will have theta or phi equals to 0 or pi, and for those values, this function again these integrals will become more simplified, and then we can solve them in an easier way. So if you are interested only in patterns of at the principal planes, these expressions can be simplified further. But and if you want a 3D radiation pattern sort of thing, so in that case, we better use a computational tool for like MATLAB to solve that. So I'll pause over here. I'll let you go through the slide. The important thing that we discussed is summarized over here. Um, that the inverse relation expressing the field at the aperture in terms of the pattern function enables us to determine the aperture field required for a specified pattern function. So for a so if since we know that the uh, field at electric field at the aperture gives us a particular pattern function, what we can do is we can use particular pattern function and engineer the electric field at the aperture. Okay, so I'll pause here, and if there are any questions, we can discuss them on this for all the material that we have covered till now. Else, we'll proceed. Uh, Now we'll continue the discussion. Starting with the electric field aperture, field at the aperture, we got the field at the point P, and then we simplify, use the approximate value of the R inside uh, the integral, the Fourier integral over here, and then we got the field at again the simplified expression for electric field at point P and the pattern function, and now the pattern function can be expressed electric field at the aperture if it is expressed in terms of the two separate functions f1 and f2, which when substituted in 161 we have the pattern function written like this. And now for the xz plane we will have phi equals to 0. If we substitute this over here, this cos phi 0 becomes cos 0 is 1, and this particular expression will be here, and sine phi is 0. So this exponential will become 1, and then this integral will be some constant c1 over here. So this integral becomes some constant over here, and this integral becomes this over here. And then we can, yeah. So we see that the radiation pattern in xz plane depends only in the aperture field distribution in the x direction. So in the for the xz plane, it only depends on the field distribution in the x direction. Similarly, for yz plane, phi is equals to pi by 2, and in this case, uh, the this f1 integral becomes a constant, and the f2 integral was present over here. So and the radiation pattern in the yz plane depends only in the aperture field distribution in the y direction. Okay. So I'll again pause over here. We just used the equation 111,163, which had the pattern function, and we tried to evaluate the pattern distribution in XZ and the YZ plane. And we concluded that the for the XZ plane, the distribution only depends upon the aperture field in the X direction, and in the YZ plane, it only depends upon the aperture field distribution in the Y direction. So I'll again pause over here, let you go through the slide. If there are any questions, you can ask them now, or we'll continue with the discussion. Okay, we'll continue. So now we have the pattern distribution with us, the pattern function, and next we what we do is we can calculate the directivity of the aperture radiator. Um, and so in the initial classes we had derived these expressions for the directivity and uh, the directive gain. So we'll use that. So to calculate the directivity, we need the maximum radiation intensity and the average radiated power. So the maximum radiation intensity can be calculated as 1 upon 2 eta naught, the distance r naught square into the maximum the maximum electric field at point P, which is now given as the integral of the electric field at the aperture. The integral of the electric field at the aperture, the whole square, and the total radiated power is the again the integral of the electric field over this aperture. Um, yeah, so we can calculate the maximum radiation intensity and the total radiated power, take their ratio, and this gives us the directivity. This is the expression of the directivity, and it is interesting again to note that for a constant uniform aperture field distribution, so this EA is constant. Um, so this will turn out to be 1, and it will be will have 4 pi 4 pi upon lambda square times the area of the aperture. Yeah. Uh, yeah, so, oh, sorry, this will not give 1. This will turn out to be the area of the aperture, because you see we have dx dy under square over here, and we have dx dy over here. So this will give us the ratio will give us the area, and so this expression 11,169 in that case um, will be in agreement with 11,121, where again we have the directive gain equals to 1 upon 4 pi lambda square times the effective uh, aperture area. I'll again pause over here. Um, Let you go through the slide. So what we did, we are trying to calculate the directivity For that, we need the maximum radiation intensity, which we calculated over here. We need the total radiated power, which we calculated over here, took their ratio, and we observe that if the aperture field is uniform, this expression 11169 is in agreement with 121, where we have the directive gain equals equals 4 pi upon lambda square times the effective aperture area. Okay, so if there are no questions on this, we'll continue. So started our discussion with aperture radiators. We we got the we cal yeah. So and we wrote down the expression for the electric field at the aperture, performed a Fourier transform to get the electric field at the point P, then used it to form the pattern function f theta phi, and then we use that to get the uh, directivity through uh, maximum radiation intensity, the power. Uh, Yeah, so that's all the steps that we went through, because we did not have the current density current distribution with us, which um, and so in the previous antennas, for example, dipole, we use the current distribution to get the auxiliary field potentials and to get the magnetic field to get electric field. So instead of doing that, we use the field distribution at the aperture to get the field distribution at the uh, far field point P, and use that to again get the pattern function and the directivity. Now, once we have the pattern function with us and the directivity with us, um, we have all the information that we tried to obtain for the other antennas, dipole antennas, antenna arrays that we had discussed earlier. So let's solve an example uh, on for the aperture radiators, and then we'll conclude this class. So in this question, it says for an A cross B rectangular aperture with a uniform field distribution. So again, we have a uniform field distribution, which implies we can use these expressions over here. Uh, and we have to find the pattern function in the principal plane, the half power beamwidth, the location of the first nulls, and the level of the first side lobes. Okay, so we'll start with the pattern function to simplify the problem, because this won't really affect because we are writing the pattern function. So we are keeping the magnitude of the field aperture, the electric field at the aperture equals to 1, and now once we set this as 1, the pattern function in the principal plane can be found from either 11164, as we saw in the previous discussion. So we can use 164 or 165. So like let's first do find out the pattern function for the xz plane, where we have phi equals to 0. So for phi equals to 0, we'll be using 164 over here, where we had phi equals to 0. Yeah, and now since EA is equals to 1, this thing turns out to be 1. This thing turns out to be 1. Now integrating this function over 1, we get this becomes B. this becomes a times some function over here. Okay, so this becomes ab sine phi by sine psi by sine psi by psi, and this psi is pi a lambda pi by lambda into sine theta. Okay, so this you can try solving this integral. This is what we'll end up with. Don't worry about the maths, but just go through these steps. So we what we are doing is, for simplicity, we set electric field magnitude as 1. Uh, Electric field magnitude as 1, and then we are using 11164 as we had done in the textbook. For phi equals to 0, we have this pattern distribution, and now f2 and f1 are equal to 1, and then we are integrating to get this value. So we have got this the pattern function as this expression. And now similarly for the other other plane, we have done it for xz. Now we need to do it for yz. For yz, we have phi equals to pi by 2, phi equals to pi by 2. And if we try solving for that, this expression, if you see, this looks very similar. In this case, this f1 will become 1, 2 will again become equal to 1. So this the first integral will become equals to a. The second integral will become b times sine phi by phi, something like this. Okay, so this is what we'll end up with again. Yeah, so in this case, okay, sine phi by phi, and in this case phi is equals to pi b by lambda sine theta. Let's just say this is phi dash, sorry, psi dash. Okay, so for x, for the x y, sorry. Okay, there's a message from Neha. Oh, no worries, Neha. The recordings will be available with you. So okay, so yeah, for the YZ plane, so we have done this for XZ plane. For the YZ plane, again we can solve the 11165, and we'll end up with AB sine psi dash by psi dash, and where psi dash is pi b by lambda into sine theta. So on that, this is just maths. You can try solving it yourself as well. We have the solution in the textbook. So we get the expression for f x z theta and f y z uh, theta as this expression over this over here. Okay, I'll pause over here. If there are any questions on this, I guess this was pretty straightforward with we just had to simplify 11164 and 11165. Okay, if we'll just uh, finish up the example and then see if there are any questions. So in the next, so we simplified the problem to get the field expression for fxz and for fyz as well. Fyz is equals to a times integral of minus b by 2 to b by 2 e power j beta y dash sine theta y dash, which is equals to ab sine psi dash by psi dash, where psi dash is equals to pi b by lambda sine theta. Okay, so we have derived the pattern function, the principal planes. Now we need to calculate the half power beam width. For to calculate the half power beam width, we have to set the we have to set this sine psi by psi is equals to 1 by root 2 to get the half power. One And once we have done that, we get psi at half power is equals to 1.39, which is again equals to pi a by lambda sine theta at half power is equals to 1.39. This gives theta at half power is equals to 0.442 lambda upon a. So this is the half power point um, in this plane over here. Now, and for sufficiently large apertures, this theta at theta sine theta half is equals to theta half. Um, yeah. So for small values, this will these will be nearly equal, and half power beamwidth will be approximately 2 theta half is equals to 0.88 lambda by a, and this is almost approximately 50 lambda by a. Yes, theta half is missing over here. That's right. This is in degrees. Never mind. Okay. Yeah. So this is and radians over here, and this is in degrees over here. I got confused. Okay. So for half power, we have the pattern function with us. We need to equate the pattern function with the half power value, and this implies this particular, since these are constants, the only this uh, we have to make this equals to half power, which is equals to 1 by root 2, and equating this to root 2, we achieve psi half is equals to 1.39. When we equate 1.39 is equals to pi a by lambda into sine theta, which give, and now by using this we get the value of sine theta as 0.442 lambda upon a, and for large apertures this will mean theta half also equals to 0.0442 lambda by a, which roughly means uh, 2 theta half is equals to 50 by 15 to lambda by degrees. Notice that we are multiplying it by 2 over here because so that this is the main beam and we have to calculate the half power, and this is theta half power. We need 2 theta half powers to get the total angle over here. Okay. And the next is we have to calculate the location of the first nulls and the location and the level of the first side lobes. So the first null occurs when we equate psi equals to pi, which means equating this equals 11,171 equals to pi, and for this particular expression we will get a corresponding theta value which is equals to lambda upon a. So this is the location of the first null, and the location of the first side lobes can be found by differentiating this expression with respect to uh, uh, psi over here, so that we get the first location, the first side lobe, the next maxima over here. Now, if so, after after the differentiation, we get uh, the look we get tan psi is equals to psi 1 or psi is equals to 1.437, and for that particular value, we have the magnitude of the side lobe as 0.217. When compared it, so this is the magnitude of the side lobe. Main lobe is 1. Uh, we can take the log value, and we see that the first side lobes are 13.3 dB down from the level of the maximum radiation. So to get the first side lobe, we are we're calculating the uh, we're calculating the we're calculating the maximas. So the first maxima, we yeah, and so then deriving this, we get tan psi 1 over here, and we get the maxima at this value. Now using that, we have the expression for we have the value for the first side lobe. Okay, so we have calculated the pattern function, the half power beam width, location of the first nulls, and level of the first side lobes. Um, that's it. I'll pause over here now. Take questions if you have from the example or the aperture radiators that we covered today. If not, we'll then end the class. I'll pause. I'll stop now over here and see if there are any questions. Okay. If there are no questions, thank you for joining. Thank you for staying with me throughout the course. Um, yeah, it was nice having all of you go through this course with me. And you do have the feedback form with you. Please fill them up, and I'll try to give return your certificates with to you by the mid of this month, or at least if not by the end of this month. I do need to check with the ISSS, who are the hosts of this particular lecture series. Um, hmm, okay. There's a question from Lucia regarding PMRF fellowship. Yes, go ahead. You can ask a question here. I'm all ears. Any question related to the class, logistics, PMRF? Fine. I mean, if I am able to answer a question. Okay, how to apply for that fellowship and what are the eligibility criteria? Um, so unfortunately, PMRF has now been stopped. So you cannot apply for it now unless until it gets renewed. So we have heard there has been discussion among the fellows that the PMRF 2.0 is under some consideration. We don't know when this will pass through, so you cannot apply for it right now. I don't know if it is renewed. Will it be renewed with the same criteria when we applied? But it uh, previously when to apply for it. When it started, you had to directly appear for the PMR interviews. Then it was changed, and you had to first get into a PMR granting institute and then apply for the fellowship. Anyways, to be eligible, you need to have a valid gate score, I believe. If you are not from a centrally funded technical institute, CFTI, and if you are from a CFTI, you must have an 8 point or 8.5 GPA. That's what it has been like. And I think the old website is still up. You can go to the PMRF website and check the eligibility criteria, but you cannot apply for it now because it's the previous PMRF cycle has stopped and they are awaiting renewal. Okay. So, any other question? Okay, if there are no questions regarding the material that we covered, I think we can uh, end the class for today, and the lecture series with it. Okay, thank you, everyone. I'll share the recording and the material soon in the WhatsApp group. And see you all soon in another lecture, which I'll probably post after coming back to India in March, February or March.